All right, so we talked about in the last chapter how sometimes the conditions aren't met. And we said that either we're using the wrong method typically, or we can just proceed with caution. But there is actually something that we can do if the success failure condition does not pass. And this is called the small sample adjustment. Okay, so instead of p hat, which we would normally use, right, especially for a confidence interval, being the number of successes over the sample size, right, x over n, we're going to use an adjusted proportion, which is another p that you get to learn, and it's p with the little squiggle on top. And I know you love that so much because you love all of the different P's that we get to use in this stats curriculum. So what we're going to do to figure this out is we're going to add in 4 fake observations just to make the sample size a little bit larger. We're going to have 2 successes and 2 failures. And maybe you're thinking, well, what if my sample size was so small that I needed more than that? I had less than, I had 6 successes. Well, it doesn't matter if your success failure condition doesn't pass because your sample size isn't large enough, then you take this course of action. Okay, so we take the number of successes and we add 2, because like I said, we're adding 2 fake successes. And then if we're adding 2 fake failures, the sample size is actually increasing by 4. And this lovely little thing on the bottom gets its own notation, which is n with a tilde on top. Okay, so then if you're trying to find a confidence interval but success failure didn't pass, this is your new formula where I'm just swapping out the p hats. Isn't that so much fun? I have to say, this is not something that I see happen very often, but I am showing it to you. Is this going to be life-changing, change every single problem you do? Probably not, but it's good to know. Okay? So number 4, surgeons examined their results to compare 2 methods for a surgical procedure used to alleviate pain on the outside of the wrist. A new method was compared to the traditional freehand method for the procedure. Of 45 operations using the freehand method, 3 were unsuccessful for a failure rate of 6.7%. Find the 95% confidence interval. So because we're finding a confidence interval, we're thinking about conditions. So we got the independence assumption, randomization condition. Is this a random sample? Well, it says they're doing an experiment, right? I think so. We're going to assume this is a properly randomized experiment. Okay, 10% condition. We have 45 operations, and let's just assume that that's less than 10% of all operations of this kind. And then we get to the sample size assumption. I bet you know what's going to happen. We're going to check it out anyway. Sample size assumption. And we're checking success failure because we're talking about proportions here. So for success failure here, I'm checking NP hat. And it says that there were 3 that were unsuccessful. And 1 minus P hat would be 45 minus 3. Or 42. That one's fine. but this one is not. It's less than 10. And to be clear here, I'm using failure as success, right? We want to find the confidence interval for the failure rate. So P is the proportion of all surgeries that failed. It's the failures. And we do not have at least 10 successes and 10 failures. So we'll use the small sample adjustment. Okay. So we're finding the adjusted proportion, which is x plus 2 over n plus 4. We said we have 3 successes, so 3 plus 2. Sample size was 45. Add 4. So that's 5 out of 49. And I know you're saying, but that's not 5 successes. I mean, that's not at least 10 successes. That's okay. This is what we're doing. So instead of using a p hat of 3 out of 45, whatever that, 6.7%, we're going to use 10.2% for our calculations. And then I'm going to say, with the small sample adjustment, it's okay to use the normal model. And a 1 proportion z interval. Okay, you don't have to go back and check success failure again. We're just going to use this new method, which we stated. Okay, so you take your adjusted proportion plus or minus z star times your standard error using that adjusted proportion. And you're just going to plug everything in. Remember, we're using the 0.102. What kind of confidence interval did we want? 95%, so z star is 1.96. And then throw those numbers in there. We're using, I messed up. We're using the adjusted sample size in here. The n with the little squiggle on top. Okay, so I'm putting 49 in here, not 45. Make sure you fix that on yours. Okay, and then that comes out to 0.102 plus or minus 0.085. So we get 0.017 to 0.187. And you're like, why do I need to do this? Well, basically this is saying because our sample size is low, the 1.96 is not necessarily going to be correct to use. So to adjust, instead of adjusting the 1.96, we're adjusting the p hat to be the adjusted proportion. Okay, so we can say we are 95% confident that the true failure rate for the freehand method is between 1.7% and 18.7%. Okay, so just that one little adjustment and everything else works exactly the same way. Next, we're going to get into some types of mistakes we could make. Okay, so there are 2 types of mistakes that we could make, not because we did the math wrong, but because we followed the correct methods and we just didn't end up with a conclusion that matches the truth. Okay, the first one is that the null hypothesis is true Remember, we're not going to know whether it's true or not. But through our method, we rejected it, right? It was true, but we found a really weird sample, and we're like, this is kind of weird, so let's reject the null hypothesis. So when the null hypothesis is true, but we reject, this is called a type 1 error. Okay? The other thing that can happen that would be a mistake, technically, is if the null hypothesis is false, but we fail to reject it. False, fail to reject. This is a type 2 error. And no, I did not come up with these names. I know they're not very descriptive, but I will give you my hint on how to remember it. Type 2 error is false, fail. 2 F's, type 2. That's how I remember it. Okay? Now, let's relate this back to the justice system. If there's someone up for trial, they're called the defendant. They can either be innocent or guilty. Does the jury know this? No. If they knew it, there would be no point in meeting, right? So this is our truth. Either they're innocent or they're guilty. If we're on the jury, we don't know for sure which one it is. Now, the jury will make a decision. What are the 2 decisions that a jury could make? They could say that the person is guilty. We call that the verdict, right? When they make a decision at the end. Excuse me. Or not guilty. Okay? If the defendant is guilty and we come to the decision that they're guilty and that's our verdict, we would be making the correct decision. Right? They were guilty, we caught them, we had enough evidence to prove it. Lovely. Awesome. If they're innocent and we say not guilty, well, that's the closest we can get to being correct, right? Because we can't conclude that they're innocent. But that would also be the right situation we want to be in. Now, if the defendant is actually innocent, but we have evidence that leads us to believe they're guilty, that would be a type 1 error. We made a mistake. They were innocent, but we decided they were guilty based on the evidence that we had. We didn't do anything wrong. We just followed the judicial process. Okay? If the defendant is guilty, but we don't have enough evidence, and we say not guilty, that would be a type 2 error. And remember, you sitting on the jury, you don't know whether they're innocent or guilty. Right? You're just doing the best with what you have. So our hypothesis test works the same way. We have the truth. Either the null hypothesis is true or it's false. Are we going to know for sure? No. What are the decisions we can make? Well, we can reject the null hypothesis, or we can fail to reject the null hypothesis. Remember, we don't accept the null hypothesis. If the null hypothesis is false and we reject it, that would be a correct decision. If it's true when we fail to reject, that's also correct. And like we defined above, the null hypothesis being true, but we rejected it, is a type 1 error. And if the null hypothesis is false, but we failed to reject, that would be a type 2 error. Okay? So, here's the definitions again. When the null hypothesis is true and we reject it, that's a type 1 error. Remember, we won't know if it's true or false. It's a risk we're taking. But there are ways that we can minimize the probability of a type 1 error. So how often does a type 1 error occur? Let's think about it. I'm going to draw a picture. I bet you can guess what kind of picture it is. You got it. It's a normal model. So here's my normal model. Okay. Say it's a one-tailed. If anything falls in this area, I would reject the null hypothesis. So that's the probability you reject null hypothesis. So any p hat that falls over there, I would reject. Now, we don't know if the null hypothesis is true or false. So the probability that I reject the null hypothesis is the probability that I make a type 1 error. Let's say alpha is 0.05. There's a 5% chance I'm making a type 1 error because there's a 5% chance I'm going to reject. So how often will a type 1 error occur? We call that alpha, which you already know about from before. Okay? Type 2 error is when the null hypothesis is false and we fail to reject. How often will a type 2 error occur? Well, we actually call this beta. This is a beta. Okay, it's a Greek letter, looks kind of like a B. This is how you write it. Okay, we won't actually calculate this, but sometimes it's given to you in the problem. Okay, it's very complicated to calculate. You could look it up if you want, but in this class, we will not actually calculate beta, but we can refer to it. All right, and now you're probably noticing as you look ahead on this page that there's a lot of vocab happening, right? So for your vocab, I would suggest you make some Quizlets so you could practice it. Here's another term for you, power. Power is the probability that a hypothesis test will correctly reject a false null hypothesis. That is this right here. This is your power. The null hypothesis is false, and you reject it, and you did the right thing. That's power. Okay? Your power can be found by 1 minus beta. Because if you are rejecting, there's a probability that you reject, right? That's the type 2 error, is that you reject. Oh, just kidding. I failed to reject. Oh, type 2, sorry. Type 2 error, null hypothesis is false. Here, it's false. We are correct, whereas in type 2 error, we were not correct. So that's how it's not exactly related to the alpha. They have some interplay, which we'll talk about in a minute, but that's where that comes from. Sorry about that. Probability of type 2 error. All right, the next thing is effect size. So if the actual value for a parameter is really close to the value you have in the null hypothesis, it's going to be difficult to determine what the real decision is that you should be making, right? So if the difference between the null hypothesis value, also known as P naught, and the true parameter value, P, is really close together, we're going to see what happens there, okay? So this is effect size, and it can be found by the absolute value of P naught minus P, okay? So, for example, let's say our null hypothesis is that the proportion, true proportion, is 0.62. We're saying P naught is 0.62. What if we find out in reality P is 0.93? What if that's the truth? Our effect size would be equal to absolute value of 0.62 minus 0.93, which is 0.31. Okay? Those are pretty far apart from each other, so it's going to be pretty likely that we figure out that our number that we had assumed was incorrect. All right, but look at this next one. If in reality, the true proportion is 0.6, let's look at that effect size. The true proportion and the value we're hypothesizing are only 0.02 apart. That's going to make it harder to make the right call. Because those are so similar, if we get a sample proportion that's unusual, it might not really tell us a difference. Okay? It's easier to make the correct decision when effect size is large. So when that true proportion is very different from your hypothesized proportion, it's going to be easier for you to make the right call and reject it. But when they're super duper close, you might fail to reject when really you should have rejected. Okay? All right, I got to stop because the bell's going to ring. So you got to check out the next video to see what's coming up next.